Okay, welcome back. So now we're going to go over the solutions to 13.3, 13.4, and 13.5. In the case of 13.3, you are asked to draw a model of matter diagrams for substances that are dissolved in water, and we really have to be aware of what type of substance they are, and that dictates how we draw them. So in the first case, we're going to be identifying if SO2 is ionic or covalent. And SO2 is definitely going to be covalent because sulfur is a nonmetal and oxygen is a nonmetal. So that makes this a covalent compound. And when you draw a covalent compound, you draw the smallest functional unit of that compound, which is a molecule. So we're going to draw the smallest unit, which is a molecule. So with this one, I'm going to identify what my shapes are going to be. So I'm going to have S, which is going to be a square, and oxygen, O, is going to be a circle to make my life easier. And I'm going to draw this as circle, square, circle. So it's going to be like circle, square, circle. And we are going to show that they are connected with a bond, like so. And then the last thing that we have to do is we have to show that they are surrounded by water. So I'm going to take X, which will be H2O, my water here, and I'm going to just draw a bunch of them indicating that these particular molecules are surrounded by water. The next one is calcium chloride, CaCl, in which case we have a metal and a nonmetal. And metals and nonmetals mean that we're dealing with an ionic compound. And when we draw the ionic compound, we draw the substance separated into the ions. So we have to remember that we're going to draw the substance separated into ions. Now, calcium chloride, CaCl, I know from the periodic table, calcium has a charge of +2 and chlorine has a charge of -1. So when I go to identify my shapes here, I'm going to say that Ca, with the +2 charge, is going to be something like, I don't know, I'm going to make it like, say, a heart because that's fun. And chlorine, which has a -1 charge, I'm going to say is a square. Now, the other key thing here is we have to draw them in the appropriate ratio. So according to the formula, the ratio up here is 1 to 2, right? So in reality, when I go to draw this, I need to draw at least 2 squares for every 1 heart. So in this case, I'm going to draw my 1 heart. Oh, I don't know if I like that. So 1 heart, I might draw 2 just to kind of show that there's a lot going on here. But I'm going to draw 2 squares for the first heart and maybe another 2 squares for the next heart. And then we're going to go ahead and surround all of that individually with water. And note that I did not draw a bond in between the hearts and the squares because these are now ions that have been surrounded by water and not molecules. And that's the major difference between an ionic compound and a covalent compound. Next one we're talking about is determining whether a solubility factor will increase or decrease a substance's solubility. So let's take a look at this one here. We have our friend Seth, who's trying to make 2 solutions, one with magnesium chloride and one with strontium chloride. He knows the one with strontium chloride forms larger crystals in the container before dissolving. So, I mean, I guess if we were to imagine this, we would imagine that like magnesium chloride crystals would be like this size. And let's say that strontium chloride crystals would be like that size. So they're really, really big. So the claim would have to be here, what's going to happen to the solubility? Will it increase or decrease? And in this case, the solubility will decrease. And the evidence for that is that we have larger crystals. We have a larger crystal size with the SRCl2. Now, our reasoning for this is a couple of things that we need to remember about crystal formation or solid formation when it comes to intermolecular forces of attraction. So, larger crystals are formed because of stronger intermolecular forces of attraction. So they are more difficult to dissolve. Another potential reason would be that the larger surface area means less solute solvent interaction. All right, so those are two potential answers, but the big thing here is you're going to get credit for identifying whether the solubility will increase or decrease, some type of evidence to support that, and then the larger crystals, and then your reasoning has to be specific to the claim. All right, so the next thing that we're going to do is we are going to interpret a solubility curve and use that information to calculate the mass of a solute or solvent at a given temperature. And my calculator's over there, so I'm going to go grab that once I get this all squared away. But this particular question is focusing on KClO3. So I like to draw or highlight that particular curve just so I can really focus in on what it is I'm looking at here. And the question is asking us how many grams of KClO3 will dissolve in 250 grams of water at 40 degrees Celsius. So it's been a while since we've done these, but like what we're really doing is we're going to be comparing the solubility on the graph to what we're asked to calculate. So in this case, at 40 degrees Celsius, we can dissolve what looks like about 15 grams of KClO3 into 100 grams of water, and that part's going to be kind of important. So the first thing I'm going to do is I'm going to take my 15 grams of KClO3. Oops, I should do it this way. So I'm going to take my 15 grams of KClO3 and put it over the 100 grams of water. Now, the next thing I'm going to do is I'm going to be comparing it to how much KClO3 I can put into 250 grams of water. So in this problem here, I'm going to put 250 grams of water on the bottom. And I'm going to be solving for like question mark grams of KClO3. So you may recall from when we did these problems earlier in this unit that we did the old cross multiplication situation, and I'm just going to kind of show that all worked out for everybody that kind of needs to see it. So I'm going to take the 15 grams of KClO3 times the 250 grams of water, which will give me 100 grams of water. That's gross. I don't know what that was. And basically grams of KClO3. Now, I'm going to combine what I can. So this is where I need to pause for a second and go grab my calculator. You can go ahead and fill this one out or finish this one while I'm doing that. So I'm going to take the 15 times 250, and I'm going to simplify that, which gets me 3,750. 3,750 is equal to the 100 grams of water divided by question mark or equals or times question mark grams of KClO3. Going to divide both sides by 100. So 3750 divided by 100 gives me 37.5 grams of KClO3. So 37.5 grams of KClO3. So the final answer there is going to be 37 grams of KClO3 and 250 grams of water. And then the last question for this particular learning target is asking us to compare the solubility at 40 degrees Celsius for NH4Cl. Let's see, so NH4Cl is going to be this one, and KCl, which is going to be this one. And we're at 40 degrees Celsius, so I'm going to go up at 40 and see that there's a point where we cross there and a point where we cross there. And it doesn't ask us to actually read anything in terms of a value, but we can see that we can dissolve more, which in this case, it looks about like 45 grams of NH4 in 100 grams of water than the what looks like to be about 37 grams of KCl. So the best possible answer here is going to be the NH4Cl is more soluble. Okay. So that's where I'm going to stop with this particular part of the video. So I've covered 13.3, 13.4, 13.5. If you have any questions, please let me know. Otherwise, good luck preparing for your quiz tomorrow.